Hello everyone, my name is Wu Dongjun, and today we're talking about curl, divergence, and Levi-Civita symbol. And before we talk about curl and divergence, let's first take a look at vector field. And what is a vector field? The definition is let E be a subset of 3D space. A vector field on the 3D space is a function of f that assigned to each point f in E, a 3D dimensional vector. So for each point, we can find a function, and it has 3 variables. So for example, we can find the origin. So like the origin is, we can find it here, and we can just find the function is this, and for 0, 0, 0, we can find the final vector is this. So for the origin, there's a vector that has 0 on x and 0 on z, and -2 on y, so it's like this. Okay, so this is the definition of vector field, and the definition of divergence and curl. We are only talk about how we calculate them, but for this topic, we're not going to talk about the geometric interpretation. So divergence is, so if there is a vector field and it is pi plus qj plus rk, it's a vector field on 3D space, and their partial derivatives exist, then the divergence is the function of the 3 variable, but we need to note that it is scalar function, which means we do so after, so we can use, this is a vector, so a is a vector, and this is a scalar function, and so we plus it, add it up, so we can see divergence is, so we can see this divergent, we can written it as divergence, or we can use this del operator, and we can add up this partial. And so for this diagram, if we have a charge and it's flowing out, so if there is a function of this, we can do the divergence, and we'll find out at this point, if this is origin, and we can find out this point will be a positive divergence. And for the curl, it talks about how the vector field is rotating. So suppose the same condition, there's an f and p, pi, q, j, and rk is a vector field on 3D space, and partial derivatives of p, q, r all exist. Then the curl of f is the vector field on 3D space, and it's defined by this. And we can write like curl f, like this one, divergent f now, and we write del, and we have a cross here, and we can written it as a 3 times 3 matrix, and you will give the same result, since we can do this one, since we can easily do it, just do this one, I, j, k, and add up them. And note that it is the divergence output a scalar, and curl output a vector. So you can give a vector and output a vector field. Okay, so the most simple geometric interpretation is, if the vector field is not rotating, if it's like this, and we'll say that the value of its curl is equal to 0. And if it is like this, and the value or the magnitude of the curl is a positive value. Okay, and so we can combine the two and make a more identity, and we can find some identity. So in the same condition, f equals to pi, q, j, and rk, and is a vector field on 3D space, and they has second order continuous derivative. Second order means you can differentiate twice, and it is continuous. Then we can find out that the divergence of curl f equals to 0. Okay, so how do we get this? We can use by clear out theorem, and by the formula we have here. So first we do this one, we get this. So this is, we can do it by matrix and expand this to ijk form, and we know that before, we talked about it before, that it is a vector field, and so we can assume this is a I component is p, q, r here, and this form we can do it a divergence. So if we do this a divergence, like this is a, we do it here, so we can just simply add this up, like p, and we partial x, and q we partial y, and add it up all, and this becomes a scalar. Okay, and so the last thing is, we can see this form, and by clear out theorem, we found out that there is some, like for example, p partial z partial y, and here is minus partial y partial z, so we can cancel it out. Why? Because by clear out theorem, if a function, multivariable function, has a continuous second derivative, we can know that we can exchange the order when we differentiate it. So these are same. So p we can cancel out everything, and q we can cancel out, since there is zx and zx, and there is for x. So sorry, for r there is yx and there is yx. Okay, so everything we can cancel out. So we left 0. So we know that no matter what component here we have for the vector field, the answer for the divergence of curl and a vector field is always 0. Okay, so but we have more identities and much more complicated combination of curl and divergence. So how do we get that? We know it is a little bit calculation here, since it is only a curl. But if it is more curl, it becomes hard to complicate. So we have a simpler way to calculate it. It's called, we use Levi-Civita's symbol and Einstein summation convention. Yeah, and there is a connected delta. We sometimes will use it. So let's see identities. So if there are two vector field A and B are on 3D space and continuous, and has continuous, so it can, and second order derivative, and we can find out that the cross product of A and B, the divergence of cross product of A and B, we can derive it into this form. And if we simply just use the matrix and use the definition above of the curl and the divergence we get here, it will be complicated, since it's a lot of calculation. So we are going to introduce the symbol to help us get the answer. So the first one is connected delta. There is it's delta, and I have two subscript I and j. So if ij is same, like it is, for example, is 1 and 1. So the value of delta is 1 and 0 is 2 and 1. So okay, it's quite simple. And for Levi-Civita, is epsilon, and it has three subscript. And if the subscript is written like, if it is clockwise, means 1 to 2 to 3, or 2 to 3 to 1, or 3 to 1 to 2, 1 to 3, 2 3 1, 3 1 2, it is 1. And if it is counterclockwise, it is 3 to 1, 2 1 3, 1 3 2, then it is -1. But if it is, some of them are the same number, so maybe like 2 1 2, then the Levi-Civita symbol is 0. So if it is, it's 0. So if it is, it's 1. So if it is, it's -1. Okay. So the last thing we're gonna talk about is, before we derive this, is the Einstein summation convention. So if there's an index like I, for example, we have the cross product here, and we usually write like this. So we can sum up everything and become a value. But Einstein summation convention tells us if there is an index appear twice in a single term, it implies summation over that index without explicitly writing the sigma. What it means? It means we don't need to really write this. We just need to write the things, because we have the same index, and these things we can also use as used on curl, divergence. We can also use on cross. So cross product. So. And another thing I want to say is, if there is A cross B I, and it means we want the I component. We want the I component. So if it is like, so we want something J. Okay. So for example, if we have a cross product, and the cross product, whole full cross product into matrix is like this, and we can expand it into IJK form. And for the I component, the cross product we want here is, we can use the Levi-Civita and use the Einstein summation. We can find out that the I components is this, because we can expand it into, because we can written like this. So if it is 2 3 3 2, and it's I, and so this is, so the first component, this is 1 for the Levi-Civita, and the second one is minus, so it's -1. So it is minus. Okay. So what about curl in Levi-Civita? So in vector notation, we can write curl in this form, like we said it before here, or in this form. So with Levi-Civita, we can write like this. So if this is 1 2 and 3, or maybe we'll sometimes write like E1 E2 E3 stands for the first direction, second and third. Okay, and so we have to have the first direction. The I stands for, the first one stands for 1 and JK, and we have partial derivative and k and j. So we expand it out like this form. So this is the exact form if we expand this, since I, and we can do this is positive and minus this one for the I components, and for the j component we are doing this minus this one. So it is the same as this one, the same. So we can use this and this to represent the same thing for a different component, for the different I, j, and k. Okay. This 3 variable, and if we rotate it if we shift it to jki, it doesn't matter. The value doesn't matter. It doesn't become e2 -1. It always 1, or is -1, or -1, or is 0 to 0. Since if it is 1 2 3 in a form, it is clockwise. So if we shift it, it doesn't change the order. So it is the same. So but if we change one of them, if we exchange two of them, like if we change I and j, it becomes I, and it is have a minus sign. So for example, if we have 1, 1, 2, 3, and this becomes 2, 1, 3, so it is minus 1 is 1, so we got a minus 2 to balance it. Okay, so this is little property for Levi-Civita. So we can use Levi-Civita and Einstein summation convention to get the identities. So proof. The first thing is by the definition, and by the definition we can use Einstein summation and the definition of divergence. This I represents this I and this I makes the summation, right? And the summation means we can add up j and partial xj and partial more. So this is the definition of divergence, like we do here. The divergence, add up the divergence of x, divergence of y, divergence of z. Okay, and this one. Okay, so and this thing is a vector, so we keep it here. But we can also use this one to represent. We can also represent this one in Levi-Civita, and like we get here. So it is the same thing. So we can just copy it here, and we can combine these two. We can just combine these two, and we'll find that we make it here and do here. And since this is just the constant, is minus 1, 0, and 1, and if we exchange it, it doesn't change the value of it, so we can just simply take it out here. And this is partial derivative, and it can differentiate this and this. And for the differentiation, we can do this. So it will be this form. This is differentiate 1, prime 1, and so for a little, so just expand it. And we'll find out that there are two forms. So, and we find out that this is really like the form of curl A, right? Because before we derive this, we have Levi-Civita ijk and curl ak, curl j, and this is the form. So, but what is the difference of here? The difference here is we need the one, like this is I1, and the first one is I. So we need to make the first subscript I, and j is the one we partialed, and k is the component. So we need to shift it. We need to shift it into k I j. So this becomes k, and we have the right place since it is I here and it is j here and it is j here, it is k here. So it becomes a curl. And for this one, we need j to become the first component since it is a divergence of j direction. So we need to exchange it, and because we need I to be here and k to be here. So if we exchange it, we just exchange two of them. So the value will be the opposite sign. So we need to have a minus sign here. So note that this is different sign, and if we rotate it counterclockwise, we will rotate it. It doesn't change the value. So we find out this, and we can make it a curl, and curl in a k direction, and this is in a j direction, and we times bk, and we times ak. So since we know that by the Einstein summation, this is k, there is twice, so we can do summation, and it is ijk. So if there is by Einstein summation, this is summation ijk. So every direction, and this is same too. So we know that this, we can find out this is the final answer. Okay, so Levi-Civita and Kronecker delta. However, we didn't use Kronecker delta, but there are very useful tools to calculate vector calculus, and if we combine them when there are scalars and there are vector, or there are scalar times vector or vector cross vector, and it is very powerful tools. If there is curl of curl A, and we'll get this, and we can use Kronecker delta and Levi-Civita to derive it. And this curl and divergence are widely used in electrodynamics and fluid dynamics, and a lot in engineering systems and a lot of things. So it is quite useful. So thanks for listening.